absolute potential at one distance away, and then simply calculate differences with respect to that. So as a footnote, I've got a page in my notes about this, and I'm almost certain there's a page in the textbook too. I'm going to post that up. I just want you to keep that in mind. Okay, so let me just remind you of this. Again, I'm not going to work through this relatively straightforward derivation in class. You've all done calculus. You know that these two relationships pair with each other. This is what we first started out by defining, and I can just flip it around and make it a derivative as opposed to an integral, and this allows me to determine the electric field if I'm given the potential. Okay, I'm going to do an example of that in just a moment. No.
Okay, so if you found the potential, but you really wanted the electric field vector, you would have to take the potential and then with respect to multiple directions, right? Or you'd have to...
It depends. I mean, yes, in principle, sure. But maybe I'm giving you a potential that is only a function of one variable, for example, and then you know that the electric field is only a function of one variable.
Okay.
And in fact, we're going to do a problem like that in just a moment. But yes, in principle, you're right. I would need to look at its derivative in all directions, or at least, let's say, three orthogonal directions. Okay. So, last example. You guys want more worked examples in class? Maybe this is too many, but I'll get it better next time. So here's exactly the scenario that may be of interest. So let's take a look at this. And I've got charge distributed in an infinitely long cylinder, radius big R. And it has an electric potential within the cylinder, so if a little r bigger than big R, that has that form. So a little bit complicated. But notice that it's only dependent on radial distance from the axis of the cylinder.
It's really...
So there are three constants associated with this, big A, big B, and big C. And there are two questions here. What then would be an expression for the electric field as a function of radial distance? That's part one. And a little bit along the lines of the footnote I just added to this, though slightly different. If I set the absolute potential at the surface of that cylinder to be 0, can you tell me something about C? And this means, can you tell me something about C in terms of the other constants? So, last example. Again, I want you to talk with your neighbor, okay? I'm going to give you maybe 3 minutes on this. And just an urging for those of you who are not yet cozying up to somebody, please do. You know, and I'm going to encourage this in recitation more as well, because based on feedback from last week, I really value you working with somebody and problems, okay? It's better for everyone. So find somebody to work on this, and then we're going to talk through it in about 3 minutes. Go.
Okay, well, so I guess it's the same question. What are you doing your derivative now by doing
I think the feedback last week was
yeah, what's your DS here? It's almost
I think you'd have to change coordinates.
there, make us do something polar. What? Well,
And also it's just the magnitude of this, I think it's we're not creating the vector, I don't think.
I mean, if I had to guess, I would just do the derivative of C by the R. I'm not totally sure why
Yeah, because I think that's okay, because it's saying the field as depends on R, so it's just the portion of the field that's in the R, the R component of the vector. So I think we're really finding a component of the electric field vector that depends on R. Yeah, so which is like part of the electric field. We're not finding the whole electric field, I don't think.
Okay.
So it's because
You're
like,
figuring out how it depends on
yeah, but not how it depends on Z. That would be the other component that contributes to the change in electric field. So we're really just finding part of the electric field.
it wouldn't even matter because these constant to this forever.
Okay. So then in that case, I guess we are finding the electric field because it's like we're only finding one part, but that is the only part.
Okay.
Like I guess if the cylinder was finite, then maybe.
So hypothetically, we can do what? Think about if B of R is equal to 0, what is C? So if it's
So then you have to solve it. You have to solve for C. That's like you just plug in R into that equation, set it equal to 0, and you solve for C.
yeah. Well, I mean, no, that's fine because then you're gonna get A plus B, so that means C needs to be like the same as negative A minus B, like C minus A minus B. R over R It's gonna be a rough pizza. I'm feeling. You sure that this is not even
Okay, 1 minute left.
Yeah. 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 I mean, hopefully, like, it's one of those things where I like dating and understand why you do it with like that. I could appreciate it.
Okay, take that quietening down as an indication you're done. All right, so how am I going to figure out the electric field specifically as a function of R to address the David Notes question? Let's get some new volunteers. Yes.
It's going to be the derivative of
Okay. Derivative of the potential with respect to R. And what does it look like?
it's going to be the constants in front times A over R plus 2BR over R.
Say that last bit again, I didn't catch it.
Plus 2BR over R. Oh, 2BR over R squared.
2BR over R squared. I'm good with that. Anything else I need to throw here? Negative, right? So that's what I often end up forgetting. I'm doing a derivative, I forget there's a minus sign up there. So that's all I need to do, okay? Now it happens to be a non-trivial but also not difficult derivative. So this is what I get. So that now is my electric field as a function of radius. So nice, right? Okay, so that's part one. Part two, how do I express C in terms of A and B? So at the surface here, for R equals big R, so what's my potential here? So I've got V at big R equals U by epsilon. So what am I left with? So I have A, obviously big R over big R, plus B, big R, little r, big R over big R squared, plus this. I'm told that this is 0 at the surface. So, there's a
Negative of those components at bigger.
Can you say it a little bit more precisely for me?
So negative a big R or just a.
Right. Okay. So what you said early on, I think was correct. Carrying on. So again, not particularly involved, but just give you an exercise in going back and forth between E and B. And then this has the value of adding the possibility that I set my 0-point potential where it was convenient, and then look at offsets with respect to that node.
So if you wanted, in this case, to like find the full vector E, then would you also have to take the partial derivative of V with respect to Z? Or,
Sure, but what do you know?
I mean, it would just be 0, right? Because
Right.
it doesn't depend.
Right. So again, very often you'll be given something that's not as complicated as a fully three-dimensional variant potential. But in some cases you will, and it'll be done in such a way that doing the derivatives, let's say in terms of Cartesian coordinates, will be simple. So I'm not going to give you anything complicated there. Yeah.
So would like the equivalent, like if we wanted to find the electric field in the previous example, would you take like the derivative with respect to like L and D to find like different components, or how would you like apply it to like?
So that one, a little bit more tricky, obviously. I mean, in principle, you could.
Or how exactly do you like decide what ds is, I guess, when you're taking your like derivative?
Right, right, that is indeed the question. I think, again, I would give you problems that have clear, they would have a form of the potential that makes that clear. So it would either be something that is explicitly in x, y, and z Cartesian coordinates, and you would simply do a derivative in those three Cartesian coordinates, or it's going to be in terms of r. I mean, in general, of course, you want to just do a three-dimensional calculation, but we're not kind of at that point in this course. So just take it as given that I will set it up with an explicit dependence to V or a clear symmetry that makes it obvious what you should do.
Okay.
Okay, so let me talk about two other things. You may have time to start talking about capacitance. First one is just to come back. Now we've explored electric potential. Actually, we come back just for a moment and return to a discussion of electric potential energy, which is where we started out. And in particular, remind you essentially of an important aspect of determining a total potential energy or total potential energy change when I have multiple charges. So I'm just going to do this for a discrete assembly of charges. Of course, it applies for continuous as well. So, here we go. So, potential energy of an assembly of, again, I'm just going to talk about this point charges. So let's say I am building up of 3-point charges. And I'm simply going to consider what happens as I bring the first one, then the second one, and the third one, and then how the potential energy of that assembly evolves. So, let's bring in the first one. And I'm just going to put them in some random places in space. So I'm going to maybe start with a charge Q1. And so bring in first charge. So this is twofold value, this very simple conceptual exercise. We're going to talk about the work done. So initially I'm starting off with empty space. The space is nothing in it anywhere in the universe. And then I'm bringing in a single point-by charge and putting it at this point. We're assuming these charges have no mass. So in terms of mechanical work, we're really not needing to worry about that. So how much work would I need to do to bring a point charge from infinitely far away and put it somewhere else in empty space? Okay, change in potential energy. So space is empty, this thing has no mass. What is that? Or actually, I'm going to encourage you to think about this in terms of work done being charge and potential difference. So let's see, let's go with Noah.
0. Because there's, I mean, the conceptual way I think about it is nothing opposing.
Right. So that's the first reason I wanted to do this. It's a little weird. We kind of think of moving things as being associated with doing work, and very often it is, because we're moving things very often in, for example, a gravitational field. There's no gravity, this thing has no mass. And so in fact we're moving this through completely empty space. And so there's actually no work being done in order to do this. So the work to bring the first one in is 0. Okay? Now, once it's in a region of space, it carries electric charge, it sets up an electric field, it has an electric potential associated with it. So now I'm going to bring in a second charge, Q2. And I'm not even specifying signs here. Obviously that determines something about the sign of the work done. And I'm going to claim that I bring it to a point where it is a distance R12 from the original first charge. So what then is the change in potential energy of this now two-charge system that I bring in the second charge? So let me encourage you to take Q1, Q2 over R squared. Yeah, that's fine. So I do some work in this case. So the work for the second one is not 0. I just want to talk about this. The work that I do, I'm an external agent now. I provide some external force, if you will, maybe to move this charge. But it's also true that the change in potential energy is the negative of the work done. I want to be very careful about this. It's the negative of the work done by the electric force. The work I do is the exact opposite of that. So this comes back essentially to the network kinetic energy theorem. So delta K is work done. My charge starts off very far away at rest. I bring it in and it's eventually at rest as well. Of course, there's no change in kinetic energy. So that means the total work done is 0. So the work that I do is equal and opposite to the work done by the electric force. Okay? So that's a concept we talked about in mechanical setting in the first semester, and I just want to make sure it's clear. So in fact, this is the opposite. This is my external agent. The work I do is equal and opposite to the work done by the electric force. So in this case, the work done the potential energy now is this. So the total potential energy in these two is now A Q1, Q2 over R12 squared not square. Yeah, messed that up. So there it is. Okay. What about when I bring in the third one? Of course, there's definitely some finite work done. And I think here it's most useful to think of it in terms of this. And think now that the potential at whatever point I'm bringing my third charge to is defined both by Q1 and by Q2. So if I wanted to write an expression now for the total potential energy of that free charge assembly, what's it going to look like? Think superposition. No? Just chewing your pen?
I guess, wouldn't you have to look at each point individually and find the difference? But like you take Q1, Q2 over R for two other points relative to
Right.
one point and then add them all together.
Right. So in fact, I need to look at all pairwise combinations. So in this sense, I would have something that looks like this. So the energy associated with the three charge system, I'm going to bring out K because it's a common feature. K1, KQ1, Q2 over R1, 2 plus Q1, Q3 over R1, 3 plus Q2, Q3 over R2, 3. I know that's not the neatest writing, but you get the idea, okay? So I'm just doing a straight superposition here. Of course, I could build this up sort of sequentially by figuring out potentials at any point as I keep adding, but this is the simplest way to do it. And what you need to be mindful of is that I need to look at all combinations of charges when I'm building total potential energy. So that's just something to keep in mind. We're not going to use it too much.
So is bringing in the third charge relative to bringing the second charge work, or total work done so far? If that makes sense.
I think it's the latter. I'm not quite sure what you said. So bringing the third one, of course I'm doing work, but how much work I'm doing depends on both Q1 and Q2 being there before.
Yeah.
So the amount that I'm adding is anywhere where Q2 appears in here. So that's the amount that I'm adding as I bring Q2, right?
Yeah.
So does that answer the question?
Yeah.
So if you think the potential energy kind of added by the addition of Q3, you're changing the potential energy of Q3 by that amount, but you're adding the potential energy of the system just by the amount of the two terms that involve Q3.
Yes.
Okay.
Yes.
Sorry.
Right. I mean, prior to 3 being in, excuse me, I got the wrong ones here. Should we use, excuse me. I thought this was. So this comes from 1 and 2, right? So that just is the energy, potential energy once I've got 2 and 1 in the picture. And then it's these two terms that have Q3 in it that get added to the potential energy as I bring the third one. Yep.
But the potential energy change of Q3 is brought by that full equation, or just the ones that involve that charge?
Just the ones that involve this charge. This was the potential energy of the Q1, Q2 system. All right, so just to reinforce this, and quick example, conceptual, and it's kind of a trick one, which is now up on the left. I see you maybe can't see the red very well. Just focus on the sketch up top. There's a bunch of parameters, some of which may or may not be relevant. So there's 2 pre-existing charges fixed in place, Q1 and Q2. And then somewhere between them is a reference point, which is a distance 2d from Q1, and it's a distance 1d from Q2. That reference point to begin with has nothing there, what I'm going to do is bring a third charge, which I'm denoting plus Q, from infinitely far away, and I'm going to put it at that point, which is a distance 2d and d respectively from the other charges. So I'm bringing in along that red line, and I happen to have made it a straight line, that charge plus Q from infinity to the reference point. Just for fun, and this is where it's an example of a problem that may contain information that's irrelevant, there are two angles defined here with respect to the horizontal, theta 1 and theta 2. So, fairly simple setup. There are some numerical values. Again, some of this is to throw you a little bit, maybe not fair, but it kind of reinforces what's important and what's not important. The question is, how much work is done in bringing that charge plus Q from infinity to the reference point, which is shown in the middle of the sketch. All right, so this one is relatively fast. I'm going to give you guys 2 minutes to talk to the neighbor, and we'll discuss it.
What work is done versus Q from infinity? Okay, so
Q1 are like the same equation that we got last time, except you wouldn't need to include Q1, Q2 with this being Q1, Q3, because that's the change in potential energy.
So okay, so I'm kind of confused. So that plus Q, is that means that when it's the full circle, does that mean that's infinity? Like when it's not?
Yeah, I mean, basically, like, it goes from one place to another, but yeah.
And then
Oh yeah,
it was
so
just
it's 2D from Q1, and this is 1D.
okay, so yeah, it would be year 1, 2, 3. That's
I don't even think you need the 1, 2, because, like, the 1 already exists. Like, you're not at, like, Q2 is already
it already
finished.
started. It already started with the system, so you didn't like have to put it in there.
Yeah.
How about that? Yeah. Okay. And then you just calculate the work that was needed to force that
Yeah.
charge into that position.
Which would be the negative potential energy.
Well, isn't it like like we're calculating W external, right? It's like how much work is needed to push it in, not how much work is being pushed back by the